啊，等开的，下到这边错哈。喂，怎么你这样？ 还有香港
马马来
马里
没有区别。
没去的，
没有开，他半价，OK 了。什么叫烟什么什么？我印度学生呢？
有多少？
I mean 我们在印地外面。
我的这可以没？
你重我想时候
论词讲完，以后完全都不可以。
哦，新
放心。
我新方式，老师。我 fail 笔试。那要去哪个学？
啥样的？要什么？要记？什么要记？
翻版的意大利。
哦，那个 Larry，看那个 Larry。ratio 哦，这个 ratio。哦。 哎，
可是他们这么平白起
是哦。什么？可以，可以，好，可以，可以。你发给我，然后我帮你加进去。你发给我那个 message，我等下怕我忘记。你发我一个 message，你说你要参加，然后发给我，然后我会报告一次，报告一次啊，找人一起打那个 action 吗？
然后
还有啊，还有以后啊，
然后我去问他，他要打
啊，等一下我们会安排我，看看，下届应该会慢慢越来越多，要挂。
画面，
我们讨论一下这样吧。
不是啊，
来了，是吧？我老爷，等一下，好，
对呀，
哦，台湾，
那脚坏掉，我都完蛋。
红错了，
可以把就可以把那个。
我觉得做的，我当时懂，我也觉得我上一堂课我也觉得我。
旁边有这种研究过文学，对，
是口罩吧？刀
都可以吃哦。他有没有查？
我那么久啊，不回来。
我也会，我也会，我也会。
不要回，不要回。
好多。太妙啊！这个。
要什么？
没有手机。
没关系。不要什么？
我可以。
我要去搜，随便来一个人就先搜。
哎，
你俩来看我了，就原来也还有奶，奶都搞不懂，那这样。知道为什么？来把题说完。太高了，标都在讲的。
Are you ready? Yeah.
Okay, good evening to everyone. So we have past 2 weeks. Okay, so past 2 weeks, we have some tutorial questions to do. But if you note that, I think we are a bit 1 week delay. So, but I didn't change the week inside the tutorials because to keep it the same as the format we have in the solution manual that I gave you. But I think we will make the replacement next week. Okay, Tuesday, 9 to 7. It's a replacement. So next week, Tuesday, 9 to 7. 9 to 11, 11. 9 to 11. Go backward in time. Hey, wait, what time is it now? Wait, let me check. 9 to 11, right? Morning. Morning, right? Sorry. It's the morning. Morning and evening both have class. I will make announcement again. Morning, right? Last time we agree. 9 to 11 next Tuesday. 5 o'clock class. Is it? Okay. Yeah. But sorry, huh? It's okay. Yeah, I mean, that one is a holiday replacement, okay? And then we haven't quite managed to change our time yet. So if there's news, I will tell you. But if there's no news, then we continue. So please do exercise. This exercise is very important. If in case if you do extra exercises, there's no solution to check, you can come to my office hour and ask me. Okay. So if you do extra, maybe in future we can add into this solution manual. Okay. So if you have anyone go through this solution manual or not? No. So this solution manual is written by my previous batch of students. We write together. So we some of them type and then some of them check answer. Okay. And you will see them in my office hour also. Some of them were in my office hour. Tuesday, Thursday, Wednesday. And just now, quite a lot of you came. I think I'm quite happy. I think around 15, 10 to 15 people come to get help. They are quite happy, I think. Are you guys happy or not? So please come, get help if you find it hard. Okay. Don't know what to do, lost in this class. Come and get help. Okay, come and get help. So so you can read something. So there's some my viewpoint towards Max. You can read. Next time maybe we can share. But similarly for this class, right? We want to write our own lecture notes, like what I told you last time. So my vision for the lecture note was we want to write a lecture note that will hopefully work for SMUN students. Okay, so we want to consider your background and then write a possible abstract algebra notes. Okay, so that they can easily understand. So we need to include. I want to make it a self-contained lecture note. Do you know what it means by self-contained? 就是自己有内容，什么意思哈？ So the meaning is like you don't need to refer other book anymore. You can just read everything there, and then you can do all the proving. Maybe matrix multiplication. All sort of basic. We include in. Does it make sense or not? Yeah. Okay. Yeah. Does it make sense? Okay. So far I think we got Ethan helping us to type now, and then we might have Adrian, and then Seng also interested, right? Lydia maybe will join. So if you are interested, right, after class, right, you send me a message, and then I think we want to make a first meeting on Thursday, and then we want to distribute out the job. Yeah, on Thursday, I think maybe after class over. Then we can try and see how to distribute out the job. Because your workload, I think, will get heavier. Okay. By the way, any one of you are using the typesetted lecture notes now? Any one of you using that? Any one of you reading those? No. If not, read one, two. Any one of you reading this notes? Any one of you using it or not? Anyone using this note to read? No. Then what you use? Huh? Might not, huh? Okay, also can, also can. But this one is a type version. Okay. 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 Okay, good. Any question you want to ask? A tutorial assignment. Anyone like need extension or not for your assignment? You need 1, 2, 3. Extension 4, 5. Let me think. 6. Extension You need extension. Huh? The last question, right? We will only finish by today. Actually, I forgot. It's about subgroup, not about group. Let me think. So you guys left the last question or what? Last question. We plan to move the last question to the next assignment. Yeah. So you just submit 3 questions for this assignment. Is it okay or not? So can you done within tomorrow? And so we move the last question to the next assignment because our lecture was delayed about a week. So that's why. Okay? It's okay? Okay or not? I will make an announcement also later. Okay, I will make everything formal in the Moodle. Okay, so for this assignment, I think I saw 3 of you submitted already. Yeah, so you can keep the last one first for this one. We will move it to the next assignment. Okay. Any question? Any other question? Any other question? If not, then I give some hint to your. Wait, let me. So let me give some hint to your assignment, right? I want to help you to recall the linear algebra knowledge. So if you go back, the book I used was by, I forgot what's the author already. But this is about the matrix multiplication. Okay, rows times column. Okay, rows times column. Okay, so to check this formula, right? Whenever you see the formula for n case, make sure you reduce to the small case to see first why is it true. Okay, don't start with the large n first. So maybe start with 2 by 2 cases. Okay, see that this 2 by 2 cases really the matrix multiplication described by this formula here, rows times column. Okay, does it make sense? So if you want to compare 2 matrices, what do? You need to compare all the entries. Okay, so you need to check that all the entries they are the same. Okay or not? Okay, so in the assignment, what do I ask you to do? Actually, I ask you to multiply 3 matrices together. Okay, so you need to do twice the multiplication in different order and then see why they are true. So I suggest if you cannot see in general formula, again, try 3 2 by 2 matrices multiply together and see what happens. And then don't quickly expand everything. Do this step by step. And then you will see that 2 ways of computation has some similarity. Okay. Does it make sense? Okay. So in our in our like this kind of pure maths course, right? We don't focus on the final answer. What we focus is the process. The process is very, how to say, intriguing. So it's very interesting sometimes. Okay. Different process, but go to the same answer. Okay, process every step step by step, and then you will see how the general formula work. Second thing is about this proposition I asked you to prove as a homework. So I asked you to prove that the inverse of an element in X is unique, but it's not enough. You need associativity to prove it. Okay. Who's the person? Where's Luo Hongri? Luo Hongri, you want to share with us why you need associativity? Maybe next class. Why? No, prepare first. No. Okay. I'll say. Okay. So Ro Hong Rui, right? Found a non-associative LOC that can have a different inverse for an element. Okay. Maybe you can try and send that picture to us, and then I try and post out. Okay. So if it's not associative, maybe you can find different inverse for an element. Okay. You can try and think about how to make it. Okay. You can think about how to make it. If it is not associative, then it is not unique anymore. Second thing is about the group definition. Still remember what the group definition is? What do you need? There are three things you need. Okay. First, associative LOC. Second, there has to be an identity. Third, every element has to have an inverse. Okay. So people might ask, what do you guys ask? Can we throw away identity or not? Okay, can we don't consider identity or not? So if you don't consider identity, right, inverse, there's no meaning already. You know why? Because you want something to compose to the identity. So if identity is not there, you don't need to talk about inverse anymore. Because you cannot check this already. E is not defined. You cannot check the properties already. And what else you can ask? So if inverse exists, meaning what? Identity have to automatically exist. Only then I can check. Correct or not? So these are the things you need to be aware of. Does it make sense? Okay. So to talk about inverse, you need to at least have identity inside your group first. Okay, otherwise there's nothing to check here. Equal nothing. Don't know how to check. You have to have identity. Okay. Yeah, so there's one time I talk about this minus and divide, right? So in pure maths, at least analysis or here, subtraction actually we can say doesn't exist. Okay, so how do we view subtraction or division? We view it as a inverse of something. Okay, for example, we view subtraction as the inverse of addition. Okay, so for example, what is 4 minus 6? Maybe you tell me it's -2. Okay, but after you learn this, right, what you need to know is 4 minus 6 is actually 4 plus minus 6. Okay, but why is it -2? 4, why is it -2? 4 plus minus 6, why is it -2? So you need to ask the question of what is -2? So we define -2 as an additive inverse of 2. It's something that when you add to 2, you get 0. So how you calculate 4 plus minus 6 actually? So by this, how should you calculate 4 plus minus 6 actually? Let me write 6. How should we get -2 properly? Using the definition of an inverse. Who can cancel with -6? 6, so you need to make 6 first. So how to make 6? Plus 2 minus 2, correct or not? So maybe you can add a -2 here first, and then add 2 at 4 like this. Okay, and then 4 plus 2, you can add them together, which is 6. So you got 6 minus 6, you get 0. 0 is an additive identity, so you get -2. Okay, actually this is the basic of MA. Okay, I'm not sure you guys do or not, but this is the basic of MA. Okay, so something like these are like natural number, real number. I think I want to add a chapter 0 to our lecture now. Okay, chapter 0. So you need to have these basic so that all these will make sense. Similarly for division, okay, so they come in a package of group. So this is what I mean. And then subtraction will appear as a additive inverse.
and then division will appear as a multiplicative inverse. Okay, so in your mind, the number system should only come with addition or multiplication. Okay, how you get minus? Inverse. How you get division? Another inverse. Okay, so I briefly talk about the history of numbers using the role of group, but this one is just for extra knowledge. It's not, but I think if you study Bachelor of Mathematics, I think you should at least listen one to this thing, this kind of thing. Okay, so you have a better idea how we construct a number system. So obviously, first of all, we start with natural numbers. Okay, you count 1, 2, 3, 4, 5, 6, 7, 8. So these are natural numbers. So here we include 0 into this natural number. Okay, and next is integer. Okay, we add like what we said just now. We have -1 as the additive inverse. Okay, additive inverse. So what does it mean here? So if you try and add these natural numbers together, right? Okay, you found that there's no way for you to get back to 0. No way. Okay, so if once I add the additive inverse, then I can get to 0 from any natural number. Correct? Like 1, -1, 2, -2, 3, -3, 4, -4. Okay, so this is how we build the integers. And this is what we call group completion. So what does it mean by group completion? So it is like you complete some set into a group. So what do we complete? So we complete n natural number into a group. Correct or not? You see, in this natural number with addition, do I have identity or not? Is it associative or not, the addition? Do they have inverses or not? No. So I add all the inverses in, it becomes a group. Okay. Okay, become a group. And then how to understand rational numbers? Similarly, here we have fraction, right? How this fraction come from? 1 over q, 1 over 2. What are 1 over 2? Multiplicative inverse, meaning what? 1 over 2 is the thing that when you multiply to 2, you get the 1 multiplicative identity. So similarly, you group complete integers using what? Multiplication. You add in all the multiplicative inverse. Multiplicative identity is already in here already, 1. So you add in all the multiplicative inverse, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over everything. But you can ask a question, Seng, 3 over 2, where it come from? You can do 1 plus 1 over 2, okay, or just 1 over 2 plus 3 times, 3 times 1 over 2, yeah, okay. Valid, right? It's just multiplication. Okay, multiplication, but 1 plus 1 over 2 is addition already. So we want to stay in the world of 3 times 1 over 2, for example. Okay, and then go to real is a bit of a story, right? Last time I told you already, right? Last time. What do? You can use your completeness axiom or use Cauchy completeness, or meaning you take Cauchy sequence of rational, okay, and then you take the limit. I think I saw your MA assignment, right? Or not? Find a sequence of rational or irrational to what? 2024, something like that. Or not? Yeah. You find a convergent sequence, okay, to a number. So this one, find a convergent sequence to a irrational. Okay, so this sequence can be different one, but they can have a same limit. Okay, so meaning what? Go up a level. This real number actually is an equivalent class of Cauchy sequence. Okay, equivalent class of Cauchy sequence. Okay, because different Cauchy sequence may be converged to the same number. You believe or not? You believe? Do you have example in your mind or not? Different sequence that converge to the same number. For example, 1, okay? You can go from left side, can go from right side. Okay, but in this world, we see every sequence that have the same limit as the same number. Same thing. Okay. So this is real. After real, you will go to complex number. I think pre-U should learn a bit of complex number, right? I'm not sure about UEC. Not UEC. I mean, did you learn complex number? No. Yeah, complex number. So what's complex number here? Actually, what does complex number do is add a number that satisfies x squared plus 1 equal to 0. X squared plus 1 equal to 0, there's no real root. No real root. This is a shame for algebra. A shame. You cannot solve. X squared plus 1 equal to 0. So what do? Algebra people very clever one. Just add the root into it. No? Just add it. 打不赢了就把它变朋友。X squared plus 1 equals to 0. We add the I, the I that satisfies I squared plus 1 equals 0 into our number system. Okay, and then you can do further quaternions, octonions. Okay, so quaternion is like 3I like that, IJK, square root minus 1. Octonion, there's something else. There's 7 more things you can add into it. And then this diagram here will contain how you multiply them. So if you multiply, for example, multiply this guy with this guy, you can go to I, go to O. Okay, if you're interested, you can look for it, but not reading, of course. Okay, so complex analysis, you will learn in complex number, you will learn in complex analysis, which is next semester. Okay, and then if you are learning more real analysis, like MA1, MA2, after that, you can do real analysis in your ME also. I think it's this semester, so it's a 09 semester. You can do this ME. Okay, and yeah. Okay, so far it's like this. So any question or not? So this is using the group's way to see how the number evolve. Yeah. Any question? Any question? The 722. Okay. So our goal hopefully today we will finish a subgroup. Okay. So today's content will be a bit creative, a bit new for you guys, a bit new mathematical objects that maybe you never played before. Because what you play before are just algebra, XYZ, and also maybe calculus. Okay, today we'll do something different. Okay, actually it's a function composing. Okay, but it's what you did every day. Let me ask you, do you clean your room every day or not? Okay, then this is a bit hard. So today is about permutation. Okay, so you move things around and then you put it back and move things around. Okay, permutation. Okay, but before that, let's do some more on the group first. We will go to the permutation group. That is the king of all groups. So let's do some more on group first, and then we will move to a specific example of group later. So first, we will learn an order of a group. Have you seen order anywhere or not? Oh, that order. Even earlier. Even earlier. Order of a set. What's that? What's that? Cardinality of the set. Okay, so what's the cardinality of a set? Is the number of elements. Okay, number of elements of G. Okay, because remember our G is just a group. Just a group. Our group is just a set. It's just a set. Okay, it's just a set. Okay, so you can count how many things inside. Our set, a group is just a special set that we can compose two things together. Okay, with LLC. Okay, so we denote this as modulus G. Okay, next. And obviously, we will call a group a finite group. And it is finite. So why is it finite? So you are counting the elements inside this group. Okay, if this modulus G is less than infinity and is infinite otherwise. Okay, let's give some example. What sort of group you already know? Right? You need to keep all these group in your mind. Always bring it in your back. Group, you know. GLN. GLN. Invertible matrix. Do you know what's the order of this group? Anyone want to guess? How big is this? Infinite. Why? Don't know. Anyone know why? There's an easier argument. Sorry? What thing? And then? How? Okay. So you mean scalar, time a scalar. So I mean you can start with the easiest one, right? What's the easiest invertible matrix? Identity, good, very good. Okay, good. Identity matrix, or maybe n of them. So how do you produce infinite number of matrix that is invertible? Yeah, like what? What's your name? Pumping. Okay, pumping. So like what pumping says, you multiply a scalar. Okay, so you can take any scalar. Where is my scalar lies? My scalar lies in R. Okay, so you can take R many of them, and then you get invertible matrix. So how many of them? R is also infinite. Okay, so you need to realize on R is infinite. Okay. So this is just if you take all of these, it's just a subset of your invertible matrix. So you contain an infinite set. Does that make sense? Okay. What else? Can we have an easier example? Easier one. Z? Z also infinite. Okay. Doubly infinite, right? So we can go positive, we can go negative. Doubly infinite. What else? Any finite set or not? Finite group. Every day you use one on your watch. That mod n, right? Modular arithmetic. How many of them inside there? N, no? Okay, n of them. And then what else? What else? Last time we gave an example of invertible function in the continuous function. I mean, invertible function that are continuous, right? So this guy inside, sorry. So this guy is a invertible function. Actually, did you realize that this f inverse is also continuous? Because how we consider this set here is a subset of continuous function. Okay, so the inverse have to be continuous. And then this is what we call, there's a terminology for it. It's what's called, so this implies that f is a homeomorphism. So basically homeomorphism means this is a continuous function, it is invertible, and then the inverse is continuous. Okay, this homeomorphism object you will learn in general topology if you go further. It's an ME course. Okay, how big is this? How big is this? Anyone to guess? How big is this? How big is this? Is it finite or not? Okay, there's someone said not finite. So, like what we did just now, can you find an infinite subset inside it or not? Can you? Can you find an infinite subset inside it or not? Can you find an infinite family of invertible continuous function? How? And they need just one, right? Fx equal to x. How to get infinitely function? Infinite function. What? Kx. Yeah, right. You can, for example, multiply a scalar to your identity function. Okay. So you change the gradient. There's more things you can do, actually. There's more things you can do. What else you can do? You can just shift your identity function. Shift it. Also infinitely many of them. Okay. So these are perfectly good continuous function, right? Invertible, right? Can you find the inverse? Okay. Yeah. The inverse should be continuous also. Right. Let me see. Let me give you an exercise to try. So how about this? We choose GL2Z2. Okay, I'll let you try 5 minutes. Try and discuss with your friend. What is this? So do you understand this notation here? 2 by 2 matrix with the entry Z2. So inside the 4 terms, right? What can you put? Only 0 or 1. Such that the matrix is invertible. Okay, see how many possibility. How many possibility in total, this matrix? Yes, 16. So are 16 of them invertible or not? Try. I give you 5 minutes. Discuss with your friend. Try. How many of them are invertible? Total only 16 only. So try. Okay, time half. I give you some hint. If you just plainly try, maybe take a longer time. I give you some hint. How about a formula for invertible matrix? Try that. When can that happen? Okay. Any anyone? Try. Anyone got an answer? 6. 6. You computed 6. Do you know which are the 6? You know? Okay. Right. Let's go through how to compute first. Okay. Let's disclose these 6 member later. So how do we go about this? So you should know that if M is invertible, what does it mean? Definition. You should be quite familiar now. What is the meaning of invertible? Oh, determinants. Okay, before that, we by group definition, what do you know? M inverse exists. Okay, but in this case, this is an inverse of a matrices. We have formula, right? We have formula for 2 by 2 matrix. So we know that M inverse is equal to what? 1 over AD minus BC times D minus B minus C A. But if I write like this, in assignment, I give you a big cross. Why? Why? You haven't explained to me what is ABCD. Where this ABCD come from? Huh? No, I mean, what this ABCD represent? These are the entry for your original M. Okay, write like this, 2 marks. Okay, so I know how to get this formula now because I need to first look for my M first. Okay, and then I know how to place them ABCD inside my formula here. Okay, so what to do? When does this matrix exist? So the inverse exists when? Only when AD minus BC is not equal to 0. But in our number system, if it is not equal to 0, meaning it is equal to 1. In our number system, there's only 0 and 1 here because it's mod 2. Okay, so in Z mod 2, AD minus BC must be equal to 1. Or maybe this one is not clear. Must be 1. Cannot be anything else already. If it's not 0, must be 1. So how many ways to get 1? Sorry? Yeah, you can go negative. But negative 1 in Z mod 2 is what? 1, no? Still 1. Yeah. Because we are in the Z mod 2 world. There's Z mod 2 just now we discussed, right? Z mod 2, how many elements? 2, lo? Okay, 2 elements. So minus 1 and 1 is in the same equivalence class. Okay, so how many ways to get 1 in this case here? I mean, if you break down a little bit further, what do you get? Maybe you get, so let's do some working. Either you get 1 minus 0, you get 1, or 0 minus 1, you get 1. Okay, and then you further break down how this 1 come from AD, how this 0 come from BC. Then how many possibility if you list it down? It's actually exactly 6. So let's list down the possibility. So AD, BC like this. Okay, so list down the possibility. So how to get 1 minus 0 here? Maybe we have 1, 1, 1, 0. Can or not? Okay. 1, 1, 0, 1 also can. 1, 1, 0, 0 also can. Okay. I think that's all already for 1 minus 0. 0 minus 1 play the same game. Same game. So you get 1, 0, 1, 1. And then 0, 1, 1, 1. And then 0, 0, 1, 1. So what are these matrices? So we can list down them now. So remember how we place our A, B, C, D again? Okay, so first one correspond to what? A, B, C, D, like this. Okay, second one, A, B is 0, C is 1, D is 1. Okay, and then keep listing. You will get the identity matrix for the third one. And then 1, 1, 1, 0, and then quickly 0, 1, 1, 1, and then 0, 1, 1, 0. Okay, so these are the 6. So can you check if you have 6 of them, are these the 6 you got? Do you have other way to get the 6? Are you using the same formula or what do you do? Same formula? Yeah. Okay, good. Okay, otherwise you just go and test test all of them. Okay, but that one will be very tedious. So a fun exercise you can do is go Z3 lor. Okay, go Z3, Z, different Z. Go for different Z. Okay, so the study of this kind of thing, if you can change the number system, this is what we did in Galois theory, AA2. Okay, you will see this kind of changing field max in Galois theory, AA2. Okay, it's also offered this, oh no, offered last semester. Is in the 04 semester. Yeah, AA2. Okay, Galois theory. Okay. Any questions so far? Oh, okay, good. So let's continue. So I think in the assignment or sometimes I already keep using this notation here. So whenever we have the composition, so whenever we have composition, for example, like A star B, okay, we will just write multiplication way. Okay, we just write it as a multiplication way. Okay, A dot B like that. Okay, to save space. So one proposition you can prove about on the group is each element has a unique inverse. So this one actually we have did it as your homework question. Okay, as your homework question. So each element in the group has a unique inverse. Because we prove that to have a unique inverse, what do you need? You need an associative LOC. But our group is defined with an associative LOC. Okay, so you can see that associativity is really important for us to study group. Okay, you cannot just throw any property away. So this one is proof last time. Next, so next there's a very useful proposition here, which is called the cancellation law. Okay, so what does cancellation law means? So in a group, okay, in a group, what can we do? If you have xy equals to xz or yx equals to zx, okay, then what do we have? We have that y equals to z, okay, and please wait for a moment. Later I'll explain what this is saying. Xy equals to x or yx equals to x, we will get y equals to identity. Okay, so look carefully what we are doing here. So look at the first line here first. So we have yz on both equation, but what do? We multiply x on both sides, but on the different side. One is on left side, one is on right side. And then what do we left here? Seems like x disappear on both sides. Okay. So they either both disappear from left side, both disappear on right side. Okay, so this is a bit like what you did in the high school. You can, for example, 6 equals to 2. You can minus 2 from both sides. Okay, cancellation law. Okay, this is what we call the cancellation law. And then this one, if you have xy equals to x, if you have yx equal to x, if you cancel x on both sides, you get identity. Okay, you get identity. Okay. So let's prove this. Okay, let's prove this. So this is a very general property for our groups. It's not like just happen in the number system. Okay, so as long as you have a group, you can do this. So how to prove this? So let's start with one of them. Suppose xy equals to xz. And then what do we want to get? We want to show that y equals to z. Okay, any idea? What do you do? How you get rid of x? Good, very good. So in group, the inverse of z, x exists. Okay, so we can multiply both sides with x inverse. Okay, to get, what do we get? We get x inverse x y equals to x inverse x z. Okay, so I'm skipping the step that we can do associativity because supposedly you have this kind of grouping, but you can associate it. Correct or not? So let me show you the one last time, and then we will don't discuss anymore. So we can associate this bracket, okay, to the right places so that we can compose the right thing together. This is very important to do associativity later. You will be using this kind of property often, this course, okay? And then identity times y and z is just y and z. Okay. So to be precise, if you write like this, right, like what I posted in your group, we see this equation as a sentence. Okay, so you need to put connective. Okay, how they are connected. So how they are connected, it should be first line imply the second line, right? Imply the third line, imply the fourth line. So you need to write down the implication. Okay, write down the implication like this. If you don't want to write in sentence, maybe you need to write saying this one is true, then this one is true. If this is true, then this is true, then this is true, then. Okay, so we skip that. Okay, so I allow we use first shorthand here. Just this implication error. Okay, and if you notice, you not only can go down or here, actually you can go upward. Okay, so everything is invertible one. So actually this is not just if then, it's a if and only if. Okay, sometimes you will get this kind of implication. Okay, it's quite strong. So actually the statement you prove here, you can prove backward. Okay, you can prove backward. But backward is obvious, I would say. It's obvious. If you already know that x and z is the same, I mean, y and z is the same, you multiply x to them, obviously the same, because you apply this, multiply the same thing. Okay, yeah. Okay, makes sense. So similarly, you can prove for all these, 1, 2, 3, the rest. Again, left as a homework. Okay, you can try it out. Okay, try all the cases now. Please try, when I say left as homework, they are using the same way to solve one. You need to try. Okay, you need to try practice. Okay, otherwise you will lost. You don't know what am I doing later. So to make you appreciate this law more, let me give you a remark. This doesn't come for free. Let me tell you. This doesn't come for free. So this cancellation law, you cannot always do it. Okay, when can you not do it? When your element is not invertible. Okay, when your element is not invertible, you cannot do this cancellation law. Let me tell you why. I'll give you an example. Okay, let me give you an example. So let me give you one example. So let's look at this example. So let's look at Z6. For example, look at what? Look at 3. Anything can multiply to 3. You get 1 or not in this mod 6. You apply anything such that you get 1 in mod 6. Can or not? There's only few cases you need to try, right? 6 things you need to try. 3 times 0, 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. That's all. Do you get anything useful or not? Will we try? Let's try. What do you get? 0 for the first case, 3, and then 6. 6 we get 0 mod 6. Okay, so notice that we use a three line equality here. Okay, to denote that we are not using the integer equality here. Okay, so this is a mod 6 equality. 339, which is 3. Okay. So this one is 12, also 0. So everything we do here is mod 6. Everything we do here mod 6. And then last one we get what? 15, which is 3 also. Okay, so very interesting here. Later we will describe this phenomenon. What did you see? The multiplication here, what? Only 2 numbers left, either 0 or 3. Okay, later we will describe this phenomenon more systematically way, in a more systematic way. Okay. But you can ask a question. Okay, so you can ask a question. So there are a few questions you can ask. So when does M invertible, okay, in a general Zn? Okay, you can ask this question. Okay, I think if you learn elementary number theory, you will know this. Okay, so you can prove that only when M is non-zero, first of all. Okay, 0 you cannot, there's no way for you to get 0 to 1 by multiplication. So, and then M is coprime to the N, okay, to your number system. Do you know what coprime is? You know, GCD is 1. GCD of M and N is 1. They didn't share any factors. Okay, the only factors they share is 1. For example, what are coprime to what? For example, let me give example here. So 1 is coprime to everything, surely. Obviously, 1, the inverse of 1 is just 1, surely exists. What else? Maybe 3 is coprime to 2 also can. Coprime to 7 also can. 5 also can. Weird one, 14 also can. Okay. Can or not? Can you convince yourself or not? What is the inverse of 3 in these number systems? Can you quickly compute? What is the inverse in Z2? How to get 3 to 1 here? 3 is already 1 mod 2. So the inverse of 3 in mod 2 is 1. Correct or not? Here, 7. What is the inverse of 3 in Z7? Let me add some Z here so that you can have a better idea. So what's the inverse of 3 in 7? 5. Yes, 5. Because 5 times 3 is 15. 15 is mod 1 in 7. Because 7 times 2 is 14. 3, the inverse of 3 in Z5? 2. Good. 6, not 6 mod 5 is 1. Here, this one easier. 5. Because 5 times 3 is 15. 15 mod 14 is 1. Okay, yeah. But you can prove it in general. This one I want to convince you first. But you can prove it in general. This is a number theory proof. Okay. If can, maybe I put it in the lecture notes, but not very useful for now. And obviously, you can ask a question. If I need all my integers, when is my Zn is a group? Okay, you can ask this question. Okay, you can ask this question. The answer is only when n is prime. Okay. Okay, I think we will discuss this again. This one I will just show you. I want you to appreciate this cancellation law. Doesn't always work. Okay, what time is it? Okay, 7:56. How about we finish one method of calculation and then we will take a break from here. Okay, so let's end with this method of calculating group composition here. So the technique we will learn now is called the multiplicative table for group. So this is a way to record all the multiplication within your group. Okay, so only when it is finite we can list all of them. If it is infinite, then it's hard. Okay, let's see how we do this. So we need a table. So how do we label? So we first fix our first row and our first column. Okay, so we'll label our first row and our first column as a list of elements in the group. Okay, so maybe it's a bit abstract to you now. So let's fix our group first. I'll give you an example. Let's fix our group as Z3, for example, and then we just add them together. So how many elements here? 3, okay, which is 0, 1, and 2. Okay, 0, 1, and 2. Okay, so this is what I meant by first row, first column. Yeah, first row, first column. It's not playing TikTok. Okay, we want to tic-tac-toe, sorry. Tic-tac-toe. Yeah, tic-tac-toe. So it's not playing tic-tac-toe. So what are we doing here? So we label. So we label the table entries using ij. Okay, we use ij to label it. So it's a bit like your matrix. Okay, ij for I and j greater than equal to 1 in less equal graphic order. Okay, from top left corner. So what does this mean? So let's do it carefully a bit. So let's say here is 1, 1, right? And then here is 1, 2, like that. 1, 3. It's really like matrix entry. Here is 1 like that. Okay, 2, 2, 2, 3. And you can label everything inside. 2, 2, something like this. 2, 4. Okay. Okay, so what do you do? So how do you fill this entry? Okay, how do you fill this entry? So for entry ij, it is a product of I1 and 1j. Okay, so for example, for this entry 2, 2, you fill in the product between 2, 1 and 1, 2. Okay, 2, 3 then. 2, 1 and 1, 3. Like that. Does it make sense? So our convention is taking the column 1 multiply the row 1. Obviously, you have different convention. You can use the row 1 multiply the column 1. But you cannot swap in the middle. If you fix column times row, then column times row. If you fix row times column, then every term has to be row times column. Because you might encounter what? A group which is not commutative. Okay. So left and right very important. Okay. So our convention is use column times row. Okay. So in this case here, so what do we do here? So for example, I rarely teach calculation, but this time I keep teach calculation. Most of them I do proof. Okay, so let me show you. Make this bigger a bit. Good. So let's look at this 2, 2 entry here. What do? You take the columns times row. So times here is plus compose, right? And then for this 2, 3 here, what do you do? Columns plus, sorry, yeah, columns plus row. Okay, and then column plus row. Okay, does it make sense? Okay, do you want to try the second row? What do you get? 1 plus 0, and then 1 plus 1, and then 1 plus 2. What third row? 2 plus 0, 2 plus 1, and then 2 plus 2. Okay, so can you see what this end result you get or not? So what's the end result you get? So you get 0 here, 1 here, 2 here, 1 here, 2 here, 0 here, 2 here, 0 here, 1. Can you see the pattern like this? The diagonal pattern. 0, 1, 2, 0, 1. That's a pattern. A lot of pattern you can see in this course. Algebra. Algebra like to play with pattern. Play with symmetry. That's the reason why this is true. Okay, so this is conventional. So you can imagine there's another convention where you add this to this. Okay, these two will potentially create two listing of multiplication. Okay. Different as in the order, okay, but all the possible answer will appear also. Okay. If this group is commutative, no matter you do row times column or column times row, they should be the same. Okay, if it's not commutative, then the table will invert. Can you imagine or not? Okay. You can do experiment next time when we see a non-commutative group. Okay, so let's fix our convention. So our convention is Our convention is, so the entry ij is the product of columns times row. So product of I1 and Ij. Okay, I1 and Ij. Okay. Yeah. So you need to fix the convention, either column times row or row times column. Cannot in the middle swap there and swap here. You'll confuse yourself. Okay, do some example and then we will take a break. Okay, so very important example we want to do here. So we do Z3 already, right? So let's go a bit further with 4 elements group. Okay, 4 elements group. So one of them is Z4 plus, I think this one is quite trivial. And then the other one is called the product group of Z2 cross Z2. Still remember or not the definition of Z? A pairs, right? A pairs coming from Z2 and Z2. How many elements inside this set here? 2 times 2, right? So it's 4 possibility. Okay, how do you add? You add component wise. Okay, add component wise. So let's see, yeah. So let's see. So let's do this Z4 quickly. You can also do on your own quickly. See we get the same answer or not. Right? Everyone calculate this table for Z4. See, do we get the same answer or not? Okay. All of us quickly calculate. See, do we get the same answer? Okay, quickly calculate, see if we get the same answer or not. Okay, so you can check the answer with me, see if you get the same answer. Obviously, you can swap the order, but typically we take the same order of these elements. List them in the same order so that you can see this nice picture here. I mean, nice pattern. Maybe for some group you need to sort order, only you can see some nice pattern, but that depends when your composition is not commutative and so on. Okay, how about Z2 cross Z2? How to add them together? You add them component wise. Okay, try and add them. See if you get the same answer. If you don't get the same answer, I need to raise your hand and ask. Because there's nothing special here. We still use the same convention. I use column plus the row. You use the other way. For these cases, if you use different convention, also never mind because they are commutative. So if you swap here and there, they should be the same. Did you all get the same calculation or not? Can check, can do inspection, can inspect. Okay. Maybe you still cannot see something useful here. Let me make it more abstract. Okay, this is why we make it more abstract. From here, too many zero, too many one. Okay, let me replace these symbols. Okay, let's replace these symbols. Let's replace these symbols by E, A, B, C, for example. You know what I'm doing? So I replace 0, 0 by, okay, let me make changes here. E is 0, 0, and then A is 0, 1. I just rename them. Just rename only. Okay, it's the same thing. I want you to see some pattern. So if you relabel this, what do you get? You get E, A, E, and then B, C, 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 B, C, B, E, A, 3. This one is B, A, A. Okay, what do you see here? Symmetric also. But can you compare to the other 4 elements group or not? What's the difference? Any difference or not? Can you see any difference? This diagonal here is 0, 2, 0, 2. But this diagonal here is what? 0, 0, 0, 0, 0. Can you see? Can you see or not? Can you see? Can you see the difference? E is the same. A is the same. We have first position. B is also the same. And then C, 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 everyone got this. And then here, yeah. Then here should be 0 identity. But here is B, E, B. So the 2B here swap to here. So this means that they multiply different way, in different way. They compose in a different way. From multiplication table here, we can somewhat see that they compose in a different way. But in future, we will prove that there are different groups. Okay. So different here, what we meant is not isomorphic. We will define it later. Okay, different group. So they have a different multiplication table. Okay. Can everyone see? Everyone see? Okay. So if you have the same multiplication tables, different group have same multiplication table, most probably they are isomorphic. Okay, but this one don't have. You see, in the middle you have A 0, 2, 0, 2, but here is all 0. E. Okay. Okay, in future we will prove this rigorously. So any questions before we break? No? Okay, if there's no question, let's break until 8:20.哦，咱们哇哦，好，然后呢？
没有听到。
其实没有差哦，对哦，I mean，你看啊，你写这样多不是，其实全部就用同一种东西就代表这样。
对，那我就去看。我觉得，完了，我也不太知道，怎么解释这两个东西？
但是排法会不一样的。对，不会有画的。对，这上面才是对啊。需要你写出那个理由，不是只是换吧？要写出那个理由，就是说，就是说，就是说他们are equal up to permutation of finite numbers。在做事情，因为你在交换，你 m 跟
然后到底是看这家
你要说不懂，我是交换的，因为你这样子都没有提示你的嘛，
为什么？
你没有每一个都告诉我，你看你就没有告诉我，
没有没有读啊，不是三次。对，第二，
对，
你要在这两个角就是在你是火车那个，然后你就写进，
对啊，
当你看这火车里面的声音，
好，对，
6块钱了。然后你要想在火车里面看的东西，
你要39，
你要跟你在外面在火车里面看的东西，
我们图
解释很多，弄啊，
你的方向。好，你要，然后那个灯放生在，
就是为什么还是要？就是他找那个vertical的，为什么要 input？
那个灯
因为什么？你在网上佛，他没有给你任何信息，他没有跟你讲哦，这个雨水从哪里开始掉，所以就说你可以在火车里面考，
因为啊，你这样子做是看不到的。M 哥，
火车里面，
然后我们通常
火车里面讲是那个往后飘，
你没有注意到吗？
现实中一点是越往后飘，
发现到这个，
火车这样哎，它往后飘。所以你在就算飘过，也是跟你那边上一样的，对，所以你去看它为什么做，它跌不是因为有意外的那种，导致是你的看到什么？
我觉得不亏，但是这个钱很讲。
没有，
来了，
有点看便宜有。哇！
可以，对，你要看这个，你要走那个差别。inside
它就它是 inside，
对对，
可是这个它就不是 inside，
有吧？哦，这个有吗？
EA，
嗯，
看
泰哥，你有没有发现到它的每一个 element 重复就是都会出现，整一排里面一定要全部出现在往下面一排要变出。对，这些都是很重要的。
这个东西不是天这种错别，这个东西就看
对，你的会只要你的会出现那样，我觉得对对，这样 OK。
要
然后我是
下来我这种店， 你的家教。
如果真的有办法，用到他聊过这家一样，因为那时候我在玩那个。
你好，我来。
就是你要一直滚，你可以就是要他看你们这样
用呢？
这比较
但是老人病。
你的这个
因为
其实就是这个，要不然这个我呢就对。是高山有这个山，
在这边的，
我在 set 里面啊，
因为我知道它是存在的，可是
不错。
所以第一个你有设定
女性有一些是那个，那为什么你打开的时候打给你？这个是因为开始做很久的，你们没讲，反派。你是吗？不要紧。
我觉得啦，因为 L OK 应该包进去了，因为我们的 LC 有跟
我们好像是
因为基础 LC 是 SS7X， 这个应该是所以我这边有一张区域是这个
这个里面有。
gamma 最标它整个什么的话，还是我 LC 对吧？
好的。
只是说我们女生去上在什么，还有变化。
我看一块比块几多，一块几个。
因为 ABC 因为 S 本身嘛 ，L 是在因为 L 这个方面喜欢最新奇，只要你两个都是从边边而上，还可以找到要火的，
还有电视公司吧。
九手九我这样子，
这一种换的范围有点说的
没有问题，因为它是到 X 的关系，这个是太高
多一个位置，对，
我灵魂灵在。
不用，如果是除非你上线，上线就要审视，因为你上线在那个 group 里面，你还是可以加，但是你加的时候还是在那个 group 里面，或者在那个 set 里面，只是说你应该是
跟 GP 的我记得我
没有。
Hello, let's come back. Back. Okay. Right. So some of you have already noticed some observation here. So if you look around this diagonal line here, if you see that it is symmetric, it hinted that this multiplication, this composition should be abelian. Correct or not? Left and right, if you swap, they should be the same. And all there's some more observation here. Did you see or not? Across every line, every row, every column, all the elements appear once again. Must appear once. Okay. In later courses, we will try and make this formal. I forgot it's in assignment or lecture, but we will see this again. Okay. In other words, what we are somewhat like permuting the group's element. Okay, you see, if it is identity, it didn't permute. But if it's A, how do you get EABC back? It becomes AECB, and so on. So there's some permutation happens here. So that's why now we need to introduce this king of all group. Okay, king of all groups, which is called a symmetric group. Okay, so this is the most important group. Or important finite groups. Okay, actually my research is related to this symmetric group. Okay, if you study this well, you can look for me. Okay, my research is about this symmetric group. So we're trying to use a symmetric group to find some link invariant. So we try to associate some invariant towards link or knots. Okay, knots, 绳结, 打结. Okay. So before that, we need to define what is a permutation is. So everyone, please be very careful. Now I'm introducing new definition here. If you lost here, then you will probably lost for the rest. So a permutation of a set X is a bijective map. Okay, so very important, this map here, bijective map. P, call it P from S to X, okay, from a set to itself. So this is called a permutation. So what is a permutation means to you? Okay, you change the position of objects, right? Okay, but in this case here, you don't just simply change, you need to do it bijectively. Okay, bijectively. Okay. So in particular, there's a special permutation we want to look for. It is the set of all permutations of indexes. Okay, I fix a special S now. Okay, what is this S here? So this S here is just consists of 1, 2, 3, 4, and then so on up to N. Okay. So this is called the symmetric group. So this symmetric group here we will denote as Sn because it's symmetric Sn. So I'm claiming something very strong here. Did you see? I'm claiming something very strong here. I said a set is a group of. So meaning what? This set has what? It has you. Okay, before that, associative LOC has an identity. Every element has an inverse. So what is the LOC here? Permutation. You need to remind yourself, in mathematics, there are really only two things you need to consider: set and function. You just need to ask you, this is a set or not? This is a function or not? So permutation is what? Is a set or function. Function is a map. Okay, so how you compose function? Just like what we did last time. Okay, you just compose function. Is it associative? Associative, right? We proved already. We prove it for continuous function, but general function is the same. Okay, general function is the same. And what else? Identity. Do you have identity here in this set? What does the identity permutation do? Fix every indexes. Okay. Okay. Maybe you don't have some image of this permutation. Let me give some example. So let's just fix ourselves for S3. Okay. Let's look at S3. So what is this? What is in S3 here? What does this S3 do? Let's say what is inside here? Okay, let me test you. What is inside S3? Function or number? Function or number? This is a very important turning point. Yeah, S3 is a set of what? Permutation. A set of permutation. So it's a function or number. Go back a bit. A permutation is what? Is a map, financial map. And then what does this map do? Bijective map between S to S. Okay, what is our S in this case? Is the set of indexes. Okay, 1, 2, 3, and then got 4 or not? No, right? So we just set at 3. Like this. Okay. So what can you do to this 3 number? What can you do to this 3 number? To define a function, what do you need to do? You need to tell me where all the elements send. Okay. Where can you send 1 to? Give me an example. 2, for example. 2 can send where? 3. 3 can send where? 1. Can I send it to 2 or not? Why not? Sorry? Sorry? You have what? You send 2 elements to 2, meaning what? This function is not 1 to 1. Okay. So we only consider bijective map onto and 1 to 1. 这就是交换咯。Okay, when you permute something, actually is a bijective map. Okay, when you do permutation, it's a bijective map. Okay or not? Okay or not? So identity function do what? Let's go at identity here. So what does identity function do? 1 to 1, 2 to 2, 3 to 3. So you did nothing. Did nothing is also called a permutation. Okay. You don't do anything is also a permutation. You do a trivial permutation. Okay, you don't change the position. Does it make sense? Is it clear or not? What's the element inside S3 or Sn? It's not the number 1, 2, 3, 4. It's a function. Function that does what? That permute n indexes. Okay, permute n indexes. So how do you permute n indexes? You need to do it bijectively. Okay, 1 to 1 and onto. Okay. Question? Any question? No question or not? Question? Question? No question? Question? Do you need another example or you okay or not? Okay. So, right. So there's a way to name this f. Okay. We use cycle notation. Okay. There's a name for it. Okay, cycle notation. So you can see that this 1, 2, 3, right, will keep appearing in the domain and the image. Okay. So how do we record this map here? There's a very convenient way to record this map. Okay. We just start from any element in the domain. Okay. Let's say we start with 1. Okay. So where does f send 1? Okay. So what do we do in the cycle notation? We just put 2 at the side of 1. Okay. And then where does 2 go? You ask yourself. 3. So you put 3 beside 2. Where does 3 go? 3 in 1. So instead of doing this, we just put a close here, telling people that from 3, we will go back to 1. So meaning from this cycle notation, we should able to recover this map here. Okay, can we recover this map? We want to try. So where does 1 go? 2. Where does 2 go? 3. Where does 3 go? 1. So this is a very convenient way to record this map. Okay, you don't need to draw this arrow. No need to write 1, 2, 3 2 times. Okay, just write it once. Okay, this is a nice thing about the bijectivity, so that we just need to record once. Okay, do you want to do some exercise? Let's do some exercise. For example, let's try x5. Let's try a map. Let's do 1, 3, 4, 6. Sorry, too many. 1, 3, 4, 5. 1, 3, 4, 5, 2. Okay, try write down this map. What does this cycle notation does? What this function do? Try and write down in your notes. Yeah, where it sends 1, where it sends 2, where it sends 3. Okay, try and write this down. Then we check together. Yeah, try right now. Let's check together. Okay, so 1 should go to 3. Okay, and then 4 is beside 3, so that means that we send 3 to 4. Okay, and then 5 is next to 4, so 4 is beside, 5 is beside 4. And then 5 goes to 2, and then 2 go back to 1. Okay, so I mind you, we read from left to right. Where this is our convention. Where read left from to right. So you need to remember this convention because of course other convention will work, but you need to see what we use. Easier to check answer later. Then we read from left to right. Left. Right. Yes. Inverse, huh? Hey, good question. What about inverse? Can you quickly see what's the inverse here? What's the inverse here? I mean, for now, the way I teach you, you should just use function way. How to use a function way? The next thing when you do composition, this one have to go back to 1, go back to 2, go back to 3, go back to 4, go back to 5. This is already fixed by what you need to do for inverse. So what do you need to do? Let's quickly construct. Good question. So nothing to check. We need to send it back to the corresponding places. Correct or not? When you compose together, only that 1 will go back to 1, 2 will go back to 2, 3 will go back to 3, 4 will go back to 4, and then 5 go to 5. Then this thing is your inverse, no? Can you figure out what's this inverse here? How to write this inverse? So let's call this G. Let's say G inverse. 1 go where? 1 go 2, 2 go, 5 go, 4 go, 3 go. So this is the inverse. Okay. Okay, so let me see. Yeah, okay. Later I will tell you how to straight away see inverse from this cycle notation. Okay, but function where should be figured out this way, correct or not? Because what we really do is just function composing. Okay, just function composing. And later I'll teach you how to straight away read from cycle notation. It is identity permutation. Okay. Later we'll use this example again. No worries. Okay. So so we need to be what? So let's give the definition to this name. So a cycle, say I0, I1, all the way up to in minus 1 of length n, okay, is an element, okay, in Sn that sends what? ij to ij plus 1. Okay, plus 1, maybe you add more than the n indexes, so we need to mod it back to n. Okay, so for oj. Okay, so do you know why we need the mod n here? So let's say if you want to go for in to in plus 1, or is it, am I doing too many things or not? I think I did too many things, right? So I think this one only stop at n minus 1. Okay, because we only have 0 to n minus 1. So if we do in minus 1, we'll go to in minus 1 in. So there's no in here. So meaning we need to go back to I0. That's what we did just now. Okay. Okay. So some remark I want to warn you first before we do calculation. So the cycle notation is not unique. Okay, cycle notation is not unique. So like what I say, you not necessarily need to start with 1. Okay. For example, what can you do? You can do, let's say, for 1, 2, 3, what can you do? You can write 2, 3, 1 also. Let's check. Let's check our definition. What does 1, 2, 3 do? 1 to 2, 2 to 3, 3 to 1. But what does 2, 3, 1 do? 2 to 3, 3 to 1, 1 to 2. Is it the same thing? Same thing, right? So it's just a different way of writing it. So it's cycle. It's really like a cycle. You can just cycle the number around. But in the right order, you cannot swap the order, but you can cycle it. So that's why we call it a cycle. So how to write identity? I think so. How to write identity? How to write identity permutation? Any cycle or not? Any cycle or not? No. If you were to write the cycle, how you write? 1 have to go to 1, or 2 have to go to 2, right? Like that. Maybe you can do this, but we can skip it. I'll just put identity. It's fine. We will understand. Okay. Yeah. Does it make sense? 1 have to go back to 1, 2 have to go back to 2, 3 have to go back to 3. Okay, typically we just put identity or E. Yeah, let's fix E. Let's fix E. Okay, fix E. ID maybe too long. Fix E. Okay, but let's say for example, in X3, okay, in X3, let's say I want to map that send, for example. Okay, so let me put this first. Hey, by the way, do you guys know this way of writing maps or not? Okay, so when you have a function, you write down your domain and codomain, and then if you want to tell us how you define this function, right? You just need to tell me where all these elements in the domain go, and then we will use a different arrow to differentiate. We will use this how to say vertical line plus an arrow to tell you that we are sending element across. Okay, we use a normal arrow for spaces. Okay, but use this vertical arrow for element. Okay, so for example, I want to write down this this function here. Let's say 1 to 1, 2 to 3, 3 to 2. How do you write this cycle notation down? What do you think? Try maybe 2, 3, and then 1 fixed, right? Okay. Usually, we just throw away this 1 that you fix. So how to say? By convention, if you don't write down any cycle for any number, we will assume that you fix those numbers. Because you can imagine, I can go S4, and then I fix 4 again. Okay, instead of writing bracket 1, bracket 4, I just don't write. Okay, so there's maybe there's some confusion here. So 2, 3 can appear in S3, can also appear in S4, and higher and greater than 3. Meaning I can fix all the other index, but just swap 2 and 3. Okay, so you need to be careful. When we write this cycle notation down, you need to ask yourself, I am in S3 or not? I am in S4 or not? Obviously cannot in S2 lah. Why? S2 you only permute 2 elements, but here there's an element up to 3. Okay? At least this guy have to stay in S3. And then for all n greater than 3, it also can be an element there. Understand? Okay, very important this language because we'll use it to compute. Okay, so next, how about 2 cycle here? Okay, so just now it's n cycle, right? N cycle meaning have n indexes. So 2 cycle means there are only 2 index. Okay, let's say I0, I1. Okay, this 2 cycle is very special. We give it a name. It is called transposition. Okay, you only change 2 things. We transpose. Okay, transpose. Change 2 number only. Okay, so for example, what? For example, just now I gave you an example, right? 2, 3. Okay, for example, 2, 3. So if it is in S3, what does this do? You simply send 1 to 1, 2 to 3, or right like this, and then 3 to 2. So transpose, you only change 2 things. Transposition. And actually, I tell you a modern way to do this. We can have string notation also. We write like this. So if you fix the top and bottom, okay, by the same order, 1, 2, 3, and then what do you do with this swapping 2 and 3? Okay, let me draw it like this. So we have 1, 2, 3, right? So 1, 2, 3, 1, 2, 3. So how do we denote this 2, 3? So 1 will go to 1. So this is called string notation. And then 2 go to 3, 3 go to 2. That's also okay. Okay, yeah. This is a string calculus we call. Okay. Okay. Yeah. Right. Okay. So there's one additional thing I want to add in this cycle here. This cycle here, this ij, okay, there shouldn't be a repeating number inside there. Meaning you cannot like 1, 2, 2. What? What does it mean by if I write 1, 2, 2? 1 sent to 2, 2 sent to 2. 1, 2, 2, right? 1 sent to 2, 2 sent to 2. Then there are 2 things sending to 2 already. No, 1 to 1. Okay, so cannot have this kind of thing happen. Okay. And you can notice that, what can you notice? This is a permutation that you cannot write as a disjoint cycle. So what does it mean by disjoint cycle? So let us define. So define what's disjoint cycle mean. For 2 cycles, I1, let's say I1. Let's keep our same notation, I0, I1 up to IN, J0, J1 up to Jm. Okay, are disjoint. Okay, are disjoint if IP not equals to JP pairwise for all possible up to where n, and then q up to where 0 up to m. And we should start from 0. Okay. So if you want to say that 2 cycles are disjoint, the number that appear in the first cycle cannot, okay, can appear in the second, can or cannot? Let me see. Yeah, cannot, because it's pairwise. Okay, pairwise. IP, JP, I think something wrong here, is it? IP cannot equals to JP pairwise. Yeah, I think something wrong here. So here should be Q here. Okay. So let me give you an example. Give you an example. So can you imagine an example or not from this definition that cannot have overlap indexes? For example, what? 1, 2, 3, 4 like this. Okay, pairwise not the same. And 1 is not 3, 1 is not 4, 2 is not 3, 2 is not 4. Okay. So I mean, just now we have a proposition, right? I think we will prove here. So an n cycle is a permutation of n indexes that is not a product of disjoint cycle. And the above here is disjoint. Or disjoint actually. Disjoint. Okay, so let's try and prove this at home. I think I'll write it inside my note. Okay, so let's try some composition here. So let's see. So how to take products of two cycles. Okay, let's see how to take product of two cycles. So this is a very important exercise. So please pay attention. If you don't understand, please ask. So first example, let's say we have disjoint cycles together. How can we compose? We just leave it like that. Okay, just leave it like that. Okay. But let's say we don't have disjoint cycle. Let's say 2, 3, 4, and 1, 2, 3. So this is not disjoint already because 2 appear in both cycle and then 3 appear in both cycle. We can try and compose them. Okay. I'll show you a cycle calculation first, and then I'll prove to you that it is really the function that we compose to. Okay, no? So there are 2 ways to get now. First way I showed you just now was using function composition. But now we are using cycle method to calculate. Okay, cycle calculation. Okay, let's see how we calculate it. So same as a function composition, we start from the right one. Correct or not? If F compose G, we do G first, right? Okay, so we start with the right one. Okay, we start with the right one. Any number you can start with. In particular, we start with 1 first. Okay, let's start with 1. So what do? 1 go where? You need to ask yourself. 1 go 2. Okay, so we need to go to 2 first. Then, so where does 2 go? You need to follow. You need to follow the other one. Okay, you need to follow the other one. Is there a reason why? No, this is a method of calculation. Later, I'll prove to you it works. Okay, so if you already use up once 2 in the one cycle, you need to go to the next one already. Okay, and then the next one will tell you where to go. And then you go to 3. Okay, so we shouldn't write 2 here, right? So we should write 3 here because 3 is the place we end. Okay, because if we use out this 3 here, we should go to the next function, but there's no more next function already. So this is the last function, so we end here. So 1 go to 2, okay, and then go to 3, end at 3. So we will write 3 here. Okay, let me try again. Let me try again. So let's ask a question. So let's write this properly. So what should comes after 3? Okay, what do? We go to the first function first. Okay, 3 go to where? Go to 1. Okay, so I use up 1 here already. Any 1 here? No. So 1 should stay. So I should take 1, 3 here. 3 go to 1. Okay. So let me draw this arrow. Let's try again. Try again. So we start a new cycle, right? Okay, let's look at 2. Where does 2 go? Okay, we start from the leftmost. 2 go where? 2 go 3. Okay, so we use up 3 here already. So we need to go to the next 3. And then 3 go where? Go 4. Does 4 go anywhere else or not? No more already, no more function already. So 2 should go to 4. And then again, where is 4? Where does 4 go? Okay, first function here, there's no 4. Okay, there's only 4 in the second function here. So where does 4 go? 4 goes to 2. But 2 can go anywhere or not? No more. So we close it. Why is it true? So let's do the function way. Let's do the function way. Let's do the function way. So first you do 1, 2, 3. Second you do 2, 3, 4. Correct or not? Okay, so let's see what does this function really do? 1 to 1 to where? 1 to 2, 2 to 3, 3 to 1, 4 to where? 4. 4 get fixed. Okay, if we do 2, 3, 4, 2 go to where? 3, 3 go to where? 4, 4 go, 1 go to where? 1, 4 go to where? 2. So all together, what happened? 1 go to 3, 1 go to 3, and then 2 go to 4, and then 3 go to 1, 4 go to 2. So it does the same calculation here. Yeah, or not? How about we try some example? Okay, give you some confidence. Okay, give you some confidence. Try some example. So let's try some more example. You try. I give you time. You compute and then later we check answer. 有没有人要不要出题啊？来出个题，我们大家一起算。喂，不要太长。Let us stop at S4. Okay, choose S4. 从 S4 里面选。来2个，不然一人一个。来，李迪一个。一不能啊。来一个塞哥。太惨了。4吧，4吧。1、4、2、3 good. Okay. Another one. 来选一个。3、2、1 Okay, good. 可以。Okay, let's compute these 2 examples. We compute together. Let's check answer. Okay. Oh, okay. Sorry. 讲一个cycle. Sorry. Okay, let's give you 2 minutes. Try and compute 2-3 minutes. And then we will go through the computation again. You need this. Okay, so today, before we finish, we will state 3 more theorems, prove 2 theorems, and then last theorem we left to next class. Okay, I think we won't reach subgroup because we can leave it to next time. And what? And that's fine because we have delayed our last question to next. Okay, is it done? Okay, maybe we can use the old way to test our calculation first. Okay, use the old way to check calculation, check answer. What should we get? Okay, let's use our old way. Okay, so this is a function composing way. So if we do 2, 3 first, where do we go? 1 have to go 1, 2 have to go 3, 3 have to go 2. And then if we do 1, 2, 1 and 2 swap, and then 3 keeps. So altogether, what's this cycle here? 1 go to where? 2, 2 go to 3, 3 go to 1. So now we have to use the cycle calculation to get 1, 2, 3 here. Okay, so let's do it. So similarly, we start from the right function first. Okay, right function do what? So let's do 2 first. Okay, 2 goes to where? So let's draw arrow. 2 goes to 3. Okay, so after you use out the 3 here, you need to go to the next 3 in the next function. Any 3 here or not? So what? So what? Keep it. Good, very good. Keep it. So you keep it. Okay, now how about 3? 3 go away. 3 go back to 2. Okay, use out 2 already. Go to the next one. Does 2 go anywhere or not? 2 goes to 1. 1 go anywhere or not? Nowhere to go already. Okay, so we stop at 1. How about 1? The first one didn't do anything to 1. Okay, that's fine. So we go to the next one. 1 will go where? 1 will go to 2. So use up 2, go to the next one. Any next one or not? No more already. So 1 go back to 2. Are they the same? 2, 3, 1 and 1, 2, 3. Same one. Same, right? Because we can keep in a cycle. Okay, we can rewrite this cycle. Okay or not? Okay. So seriously, you don't need to start with 2 or 3 actually. You can straight away start with 1 also can. Okay, you can also start with 1 also can. You will get 1, 2, 3 also. Okay, you can calculate starting from 1. Because what are we doing here with this arrow? It is actually doing this arrowing here. Did you realize? Did you realize or not? When we do this calculation here, when we ask where 2 go, 2 have to go 3 first. Go to 3. And then we use the next one. Does 3 go anywhere else? No, 3 stop at 3. So 2 to 3. Can you see this composition here? Okay, and then next you ask where 3 go. So you start all the way from the first composite. Where 3 goes? 3 goes to 2. And then the next one will send 2 to 1. Is it true? See? 3 goes to 2, 2 goes to 1. Okay. So what we do in this pink, blue, green arrow here, right, is actually doing the function composing. Okay or not? So you might ask, what's the advantage? Advantage is we don't need to write the whole thing out. Okay, we just look at number, how they jump. Okay, so like what I said, this cycle notation is really compact. It not only tell you how the function get defined, even when they compose, you still can calculate it. You don't need to write this down. This one you can keep in your storeroom already. Okay, but of course, if you want to check whether your calculation is correct or not, maybe you can bring it up. You have 2 ways to do and then check they agree or not. Okay, does it make sense? Okay, so let's quickly do this using cycle notation. Maybe I do it and then you check. So where does 1 go? 1 go to 3 first, and then second 3 goes to 2, so stop at 2. Where does 2 goes? 2 goes to 1, and then 1 goes to 4, so stop at 4. Where does 4 go? Only the second one control the 4. 4 to 3, and then nothing else. 3 stop. 3 goes to where? The first one have to manipulate 3 first. So 3 goes to 2, and then 3 backs to 1. So you need to close it. Anything we miss or not? I think nothing. So a sanity check. So go back and do your sanity check. So whether 1, 2, 3, 4 really get sense to 1, 4, 1, 3 or not. Okay. Do this composition. Okay, try and check this composition. Okay, they should agree. Okay, does it make sense? Understand? Understand or not? Please check out. Go back and check out. Okay, good. So let's do proof of two more theorem and then one statement. We will finish. Okay, actually there's one observation you can make here. So proposition. So let sigma and tau be two disjoint cycle, meaning recall what is disjoint cycle means. They don't have the same indexes appearing. Okay. Then what do? You can commute them. Okay. Remember there's an example I gave you, right? You need to keep example in your mind to see these abstract statement here. 1, 2, 3, 4. What does it mean by this statement here? We can rewrite it as 3, 4, 1, 2. Does it make sense? Okay. But what is this amount to? So if you write down 1, 2, 3, 4, what's this map here? It's just sending 1 to 2. So I mean, if I want to write it like this, let you see what happened. 1 to 2, 2 to 1, 3 to 4, 4 to 3, right like this. But what is 3, 4, 1, 2 does? It's really the same thing, right? Just like this. The arrow doesn't change. Does it make sense? It's the order that we do the function change. Okay, to be precise, what can we write here? To be precise, what do we do? So what do we really do here? So if we do 3, 4 meanings what? We already fix 1 and 2. Okay, we fix 1 and 2. Okay. But what does 1, 2 do? 1, 2 is you swap 1, 2, but keep 3 and 4. Like this. Okay. So if you compose them together, what does it mean? So you will do this first and then do this. Okay, so all together, can you see something like this? Like this, like this, like this, like this, and then like this, like this, like this, like this. This is the string diagram that I drew just now. Okay. Make sense? And then this is equal what? This is equal to if you swap the order. Okay, swap the order means what? You can do this one first, copy, paste, one of them. Okay, so instead if we do 1, 2 first, and then do 3, 4, can you see the string diagram or not? What happened to the string diagram? If we join them together, it's the same. It's the same. So wait, let me see. Sorry, I think we changed the order already. We should do 1, 2 first. 1, 2, and when I how should I move this? We do 1, 2 first. So a bit confusing here. Why is it confusing? You need to remember how you compose your function. Okay, so what do we get in the term of string diagram? So you cross first and then do straight, and then you straight, and then do cross. So these two are equal. Okay, meaning what? Your cross can move forward, backward. Okay, but in terms of function, they are the same. Okay. Actually, this is a very advanced calculus here. This is a topology, what we did here. They are the same. We can move this crossing forward and backward along this straight line. Okay, there's some topology involved here. But can you see that in terms of function, they are the same? And right. Okay. In the end, what they do, they just swap 1, 2, and then swap 2, 3. No matter you swap which one first. Does it make sense or not? Make sense? Okay. Okay, so I think I don't want to prove it later. Torture your brain. Is it torturing? Is it torturing or not? Do you want to prove it? Yeah. No, next time. Okay, next time. Okay. Let me convince you these statements are true first. Okay, then next time I prove it to you. Okay, sound good? Okay, two more statements. Two more statements I want to show you before we finish. We don't prove first. Don't want to torture your brain at this late night. So next statement is any cycle in Sn, okay, can be written as the product of transposition. Okay, actually just now you see one example of this already. Do you remember the calculation we did? Let me swap out. So 1, 2, 2, 3. Okay, 1, 2, 2, 3. What do we get? We actually get 1, 2, 3. So this is the instant of taking this one like this 3 cycle as a product of 2 transposition. Okay, can you see? Can you from this example? Can you see a formula or not? Guess a formula. Yes, I guess. Mathematics, you have to guess one. Intuition, grow intuition first. You want to guess? True or false also never mind. Guess only. If I give you 1, 2, 3, how to write into product of 2 transposition? You want to guess? Can you see formula up over here? Let's say I write IJK lah. Okay. What should I do? Yes, IJK. Yes, you should prove this. You should prove this. This is true for general. So let's say A1, A2, A3, up to AN. What can you prove? You can prove that this is equals to A1, A2, A2, A3, and then so on. Okay, yeah, we can prove one. But it's a very easy proof. You just check. If this one is equal as a function, right? You just need to check whether this side send A1 to A2, whether this side send A1 to A2 or not. Let me quickly argue. Quickly argue, very quick one. Here, send A1 to A2. Nothing else already. No more here. Must stop already. But here, where is A1? A1 doesn't appear in the front. There's only one place A1 can go. A2. Then you can see where A2 go, A3 go, A4 go, A5 go. Okay. This is how we argue. Okay, last one. Last one. Last. Okay, really last already. So if yeah. Question? Now it's past 9 o'clock already. What do you mean? Oh, we can leave to next class. No, I want your brain to be occupied by this thing first. Okay, next time when I introduce it's better. Otherwise, it's counted new next time. Yeah, otherwise it counted new next time. The others one. Okay, maybe next time we'll consider. Okay, so if a cycle can be expressed as the product of even, okay, if I don't want to say cycle, if a permutation, okay, can be expressed as the product of even or odd number of transposition, then if you have a chance to replace it in any other way or any other product of transposition again, let's call this permutation sigma, okay, equaling to sigma. Then it also must be even or odd. Okay, I give you an example. Please remember this example in your mind, then next time when we do proof is easier. Okay, so give you an example. One very easy example we'll see already. 1, 2, 3, 4. Okay, the other way to write this is obviously 3, 4, 1, 2. Okay, but how about the others? For example, 1, 2, 3. Okay, just now we know that this can be written as 1, 2, 2, 3. But you also can check that this can be written as 2, 3, 1, 3. And also can be written as 1, 3, 1, 2. I think these are the only way. 1, 3. I think these are the only way already. So whenever you want to split them out, if they split into even number of permutation, always all the other way is even permutation. If it is odd, then always is odd. This is a very special observation that we can make for this group here. It makes sense? We only concerned about product of transposition, not 3 cycle, 4 cycle, 5 cycle. It's transposition here. Very important. This one is concerning transposition. Okay, product transposition. If it is even, if it is break into even, always different way of writing must be even permutation. If it is odd, maybe give you an example. Let's say 1, 2, 2, 3, and then 3, 4. Okay, what does this compose to? 1 to 2, 2 to 3, 3 to 4, like this. Okay, and then all the other way, if you do it again, it should be 3 again. I mean, in the odd permutation. Okay, odd. Okay. Any question or not? You know why odd? Because I can do cheat, I can just add an identity into my expression. Okay. I can do cheat. Okay. But these two compose to identity. Right or not? If you swap 1, 2 and then swap 1, 2 back. Okay. So even stay even, odd stay odd. You never write this in terms of 2 product or 4 product. Never. We will prove it. We will prove it. Okay, maybe C, for example, don't know how to prove, but we will prove it. Okay, or not? Any question? So these 3 statements, we will do the proof next time. I think this is the first abstract proof you will see. Okay, see you on Thursday.